Right, our next session is called Secrets to Building with Foundation Vision Models. And our next speaker is Joseph Nelson. Not only is he the co-founder and CEO at Roboflow, providing developer tools for computer vision, but his work has impacted over 100,000 developers worldwide. No small potatoes. With impressive backing from prominent names including Y Combinator, Craft Ventures, and the founders of a little startup called OpenAI, Joseph is a driving force in the field. So prior to his endeavors at Roboflow, Joseph co-founded and successfully sold Represently, an NLP startup. And his passion for sharing knowledge led for him to teach at the Great General Assembly. And he has contributed his expertise to various technology companies. Now, today, Joseph is here to shed light on a game-changing concept: foundation models as a cheat code in AI development. Sounds good. These models, epitomized by Clip from OpenAI and Segment Anything by Meta AI, encapsulate a wealth of knowledge ready to be harnessed for your applications. In this session, Joseph will guide us on harnessing these powerful tools alongside YOLO V8 and open source resources, unlocking boundless potential for your next application. Ladies and gentlemen, please join me in welcoming a luminary in the field for what promises to be an enlightening and transformative session. Give it up for Joseph Nelson. Thank you.
Hey everyone, audio okay?
Perfect.
Awesome. Visuals looking good?
Yes.
Wonderful. Well, thanks everyone for tuning in today. I'm looking forward to today's discussion on foundation models, open source, and all things YOLO V8. I appreciate the esteemed introduction. As noted, I'm with Roboflow, and we enable you to build better computer vision datasets, models, and deployments faster. A little over 250,000 developers build with our tools, and we're huge fans of enabling folks to be successful with Ultralytics, YOLO V8, and the entire ecosystem. So I thought today what would be interesting is to give some quick overview into why computer vision, how computer vision, and the advances in foundation models generally. Now, I think most folks here are practitioners of computer vision already, but it's still fun to kind of reflect on, why we do what we do and what's possible and some of the example projects that are fun along the way. Computer vision at its core means that anything that we see can become software. And at Roboflow, we say our mission is to make the world programmable. That sort of gives superpowers to making the world more interactive, more efficient, more engaging, more fun, whether that's identifying ways for retailers to know what's in stock, out of stock, or snap filters to interact with the world and make things be fun, like dog filters or all sorts of face swap, to businesses being able to know what's going, what logistics and supply chain sort of needs they have. And for things that are already software, there's the opportunity for adding magical experiences for your users. So a few things that have been built with Roboflow, and a number of which also with the YOLO V8 family of models. First and foremost, flame-throwing, weed-killing robots. Here's sort of a photo here where not one, but actually two users have made capabilities for creating robots to kill weeds in the lawn. Or someone else made a cat exercise machine. They strapped a laser pointer to a robotic arm, trained the model to identify where their cat is in the scene, and then constantly pointed the laser pointer 10 feet away. They called it an exercise machine. I might consider that something else, but it was fun all the same. Or guiding drones, getting a sense of from aerial imagery where there's given solar panels across homes, or doing drone navigation. Or actually doing things like automated OBS controllers, Open Broadcast Studio, for basically changing camera angles or making logos appear, or things of this nature. So here you can see an example demo where this is actually running fully in the browser using RoboflowJS, which is a wrapper around TensorFlow.js, for creating and delivering in-browser experiences. Any canvas can be passed to this capability, and it's super fun. Or a couple years ago, Roboflow, the team, we for April Fools, we wanted to save the world from Rickroll. So we made something that sees Rick Astley's face, and if it sees his face, it muted your computer and blacked it out, so you could never be Rickrolled again. Now, we actually got our start building AR apps, so I think it's fun to kind of show this history. We made this app that in 2017, when Augmented Reality Kit came out, solved Sudoku puzzles. To be clear, this totally ruins the game of Sudoku. This is more to demonstrate what's coming and what's possible in the world of computer vision. This app actually won AR App of the Year from Product Hunt and inspired a lot of the tooling that we now work on so others can make similar applications. So a last sort of thing to shout out is an example of building with foundation models. So we built a game called Paint.wtf that grew to 120,000 players in its first week, actually 7 requests per second at peak in its first week, which is sort of like an AI Pictionary. The user's given a prompt from, at the time, GPT-3, like draw a giraffe in the Arctic or an upside down dinosaur. You give an in-browser canvas to draw that, and then Clip, which is a OpenAI trained model that understands 400 million image text pairs, would rank and say which image is most similar to that text prompt. And as noted, it went mini viral and folks enjoyed playing with it. It's actually still live to this day. Okay, so we talked about all sorts of things and inspiration that folks are building, but how are they building those things and where does computer vision fit in? I think most folks are probably on the computer vision is useful train. So let's talk about how folks often do these things. At Roboflow, we have a platform that folks will use to build in a large open source community for people to start from pre-trained models, 200K open source labeled data sets, and everything in between. That includes 250,000 developers to half the Fortune 100 building with these tools capabilities. You can do things like use segment anything to auto-label your data in browser, or use Autodistill, an open source framework we maintain to take advantage of foundation models like Grounding Dino to then auto-prep a data set and train a task-specific model like Ultralytics YOLOv8. And you can also deploy. You can directly have a hosted API or even a container that you can take and run for accelerated inference on given runtimes, whether that's going to be on an NVIDIA Jetson, in browser, or on iOS SDK, and many things in between. So the core primitives are datasets, models, deployments. I said we're going to talk about foundation models. And I think foundation models change the paradigm for how we build computer vision going forward. There used to be that you'd always start with having a freshly collected data set, then you train your model, then you do deployments. Increasingly, there are already models that exist to accomplish a given task that you have in mind. And these are foundation models. Foundation models are those that are sometimes multimodal, like for example, GPT-4 now supports vision inputs, or Bard. And sometimes they're a single modality, like Blip2, Salesforce's model for doing captions, or OpenAI Clip for doing zero-shot classification task and calculating embeddings. But the core insight here is sometimes you can actually start with a model and start with a deployment and see where your model fails, and then go back and continue to improve your data set. At other times, you may want to use the large model and distill its knowledge down into a small model, like a task-specific object detector, instance segmentation model, and use that model for the use case. So I want to provide some guidance and give some clarity about when you might use each given task. So scenario number 1, let's pretend that we have a foundation model and we can use it as is. In other words, let's pretend we might not need to do any retraining. Example models that fall into this class of problems are things like OpenAI Clip, Segment Anything, Blip2, Doctor for OCR text recognition. Use cases for this might be things like content filtering, or image captioning, or video and image question answer. And the assumptions here for building with a foundation vision model is that you already have access to large compute, and usually the internet, because you're going to run the foundation model on a hosted server somewhere. But you don't have real-time requirements, because usually the foundation model takes a bit longer to do inference, or if you're calling an API over the web, there's maybe a few hundred milliseconds of latency. And maybe we don't need to build some of our own IP. We just need a model that works. Content moderation is a great use case. Out of the box, Clip can do things like content moderation, and it helps fuel and increase the quality and quantity of quality images and data sets. Maybe you're like a Shopify and you want to see if someone uploaded an image of shoes, or of wardrobe, or of something inappropriate. You can automatically zero-shot, make sure that the image uploaded matches the rest of the text description the user is using for their product. Now, semantic search is kind of a go-to use case here, and I have a blog and tutorial as a follow-up for this. For the sake of time, I'm just going to leave this as an example use case in scenario 1. Now, scenario 2. Scenario 2 might be, we think we have a model that works as is, but in fact, it doesn't. And I think this is actually where the majority of scenarios are going to grow to. So, again, we actually have a similar set of models that we might want to try out in the similar family of models. But the use cases actually might be a bit more extensive. Generally, things that are less known, maybe object tracking or counting, or maybe the content filtering, but we need to get more specific with the content. In this context, we have assumptions like we have an industry-specific data set or problem that we need to know more about. Again, if we're going to use a large model in production, we may need access to the internet to use that large model and use large compute, or we could distill down and fine-tune our own model like YOLOv8 for the capabilities of creating a task-specific model. And we may want to be building our own IP in a data set or model over time. So an example of this might be something like environmental monitoring and species identification. A foundation model might know, for example, a bird or even like a flamingo or even a specific type of flamingo, but it might not know this individual genius or very specific name that a biologist may be concerned with identifying of a species. So you might use the foundation model to say, okay, generally we're looking at a bird, but I want to do a task-specific model to say which bird we're using. And this is where we've introduced an open source framework called Autodistill, where you can use a base model, something like Grounding Dino, SAM, DTIC, to auto-label a video or image for you. And then with that labeled data set, you can train a task-specific model and add to that data set and use that task-specific model in production. Not only does that allow you to be more cost-effective, but it allows you to accelerate your workflow so you can almost start at the end. Now, another use case that I'll breeze past and share a link in the follow-up is I made this rock, paper, scissors app where you play rock, paper, scissors against AI and it runs fully in the browser. If there's time during Q&A, maybe we can talk more about this. Now, there's still scenario 3 where there's not a foundation model that we can use and we have to train our own model from scratch. This is kind of the traditional workflow with which we're familiar, where we're going to need to collect some custom images and video. We're going to need to prepare that data. We're going to need to validate the model's performance against that data. We're going to deploy that model, and then we're going to do continuous improvement amongst that model, whether with active learning like we just heard or other sorts of techniques. So common use cases for this might be like a domain-specific problem, like maybe identifying machine parts, or we have maybe deploy conditions where the model needs to run in real time or on limited compute. The types of models we might use here is certainly like the YOLO family of models, ResNets, EfficientNet, Vision Transformer, for some of the ones that are smaller. And so some assumptions here is that we want our own specific model. We want to build our own IP. We want to basically take what a big model knows and turn it into our own custom model. And basically, the way I kind of like to describe this is big models know a lot about a lot. A lot of the time, businesses need to know a lot about a little. And if that's the case, you can use the knowledge of a big model to create the knowledge of a small model. Now, a use case for this, an example, in addition to machine parts, might be like a chess piece detector. Maybe you could argue there's already models that exist for chess piece detection, or maybe you could say that chessboards are so different in the boards and pieces. There's like Harry Potter chess, there's official US Chess Federation chess, there's all sorts of variation, life-size chess. So you might need to do a specific model from the get-go. Now, as noted, we work on providing tools to make each of these processes easier, whether that's going to be data sets for using segment anything for auto-labeling things and QAs and workflows and smart collection, or models for doing custom training, whether you have a model from the model registry that we maintain of a few dozen models or Hugging Face or anywhere else, or deployments, whether you want to deploy to a hosted API, maybe a container, maybe you want to take it and run in browser and continue to monitor these improvements. Roboflow Universe is noted as one of the largest collections of open source vision data sets and pre-trained models. So it allows you kind of start at the end, whether you have a labeled data set or an existing model endpoint amongst the 50,000 plus of tasks that you might want to do. So the last thing I want to leave you with before opening for Q&A is recapping some of the tools that you should take advantage of for doing things like this. Autodistill is our framework for doing open source distillation of foundation vision models. And I have that pulled up here. Here's the GitHub repository. And the example we show is passing a video and auto-labeling and producing an example that labels bottles of milk and plus the bottle caps on those milk. And you can kind of see what models are supported for base models, meaning a big model you can learn from. Grounding Dino, YOLOv8, SamClip, and then you can train a smaller task-specific model. This is fully open source and a framework that you can use to either auto-label or even auto-deploy with a single command from a given video or image. Supervision is open source utils for computer vision. So Supervision is a popular library for splicing and dicing detections, tracking how long things are in a zone, doing data set conversion, some model evaluation, and it's a set of utilities that increasingly folks will use in tandem with other capabilities. Inference. Inference is our open source container that we've released so folks can take and run inference on their target device. Notably, the key thing about inference is at Roboflow, we've served hundreds of millions of API calls across tens of thousands of models. We took those learnings and we built them into the way that we might want to use and deploy models. And so this is basically provides a server so you can pass any image or video and get back your detections. That standard set of APIs mean you can load any sort of model, whether that's going to be your own maybe YOLOv8 model, maybe you're going to load a clip model, gaze detection, SAM, whatever you want to do. And it makes it really straightforward for basically getting stood up with that model, updating that model over time, and monitoring that model's performance. Notebooks. Notebooks is where we have a series of tutorials and walkthroughs, collab notebooks, educational resources, and it walks through all sorts of various tutorials of custom training or computer vision skills like tracking objects. Universe, which we talked about, and then app.roboflow.com, which is the hosted set of tools for using these sorts of capabilities. So with that in mind, I want to turn it open to question and answer, and welcome any sort of discussion thoughts that folks may have around foundation models, around open source surrounding YOLO V8, and capabilities to kind of start at the end as it relates to how us as computer vision practitioners can produce high quality outcomes faster.
Tremendous. But first, a big round of applause for Joseph Nelson. That was such a great presentation. So much great information in there, lots of resources, lots of links. That's what we like to see. Okay, do we have any questions here in Madrid or joining us from Talia at the back there? We have questions via Talia. Thank you. Take it away.
Okay, so Joseph, what methods can we employ to track the performance metrics of the model during training on the RoboFlow platform?
In RoboFlow, when you train a model, you can either pull your data set and train on your own infra, or use hosted GPUs that users have available and access to in RoboFlow. When a user trains in RoboFlow, you're able to get real-time statistics on, for example, object detection models are measured in mean average precision, recall precision, and then you'll also get a confusion matrix of showing where the model may have failed, where the model was successful. We also recently added the ability to see embeddings, so you can see patterns of failure amongst the types of images that that might be causing success and failure. And note that models can be uploaded to RoboFlow if you train them from elsewhere, which means you can still get these quality insights on your data set, regardless of where it was trained. So hopefully that gives some context.
Fantastic stuff. Absolutely great. We've got a question from the room. If you could introduce yourself. Thank you.
I'm Marve from Hugging Face. So I experimented around the knowledge distillation with a toy example, and it was what it was essentially doing was that it was taking KL divergence between the teacher and student output logics. And it was a very much a toy example, like distilling ResNet to MobileNet, but when I benchmarked them, I couldn't really observe a lot of change. I want to ask firstly, if you have any suggestions around which knowledge distillation technique is the best, and if a big foundational model does make a difference compared to something small like ResNet. Thank you.
Yeah, this is a great question. Distillation refers to taking what one model may know and then almost like slicing out the part of its knowledge into a maybe smaller model or a specific architecture. In your question, you noted that you were distilling ResNet into MobileNet. ResNet is a task-specific model, as similar to how MobileNet is a task-specific model. Some of the most successes that we've seen with distillation does rely on, as you alluded to, taking large foundation vision models or even multimodal models and using what those large models know to auto-prepare a smaller data set for a different type of task. Now, it's not bulletproof, and I think it reflects some of the current limitations that we have related to what foundation vision models and multimodality is able to do. Multimodality and large models are not infallible, but they basically help curate a data set so you can almost only focus human effort on places where the model is kind of already failing. And so some successes that we see are, for example, using grounding dyno and SAM as what we'd consider your base model. And then a target model could be actually a ResNet or a MobileNet. In this example, you would have the base model of SAM producing masks. And as you know, SAM produces masks, but it doesn't label those masks. And so you combine SAM's masks with the predictions of grounding dyno, which is a zero-shot object detection model that does provide estimates of class names. And between those two things, we might be able to get bounding boxes or instant segmentation masks that are labeled with a class name for a wide array of objects. We haven't found that this is like perfect, and certainly requires, I think, continued improvement in research and development. Though for very, very common things, it certainly accelerates a workflow. So to be specific and actionable with your question, yes, we generally find that larger foundation models as the source of where you're distilling from produces better results than using a small task-specific model and another small task-specific model in pursuit of distillation.
What a great question. Thank you, Merve. And we're going to wrap it up there, please. Oh, do we have to move on? Because I think we might have reached, I'm sorry, we've reached the end of time, but maybe if you reach out to Joseph afterwards. We've got one more question, but we do have to move on with our program. So listen, thank you so much for using AI to save the world from the curse of rickrolls. That is very, very impressive work. Thanks for everything you do. A big round of applause for Joseph Nelson. Thank you.